Hey, today we'll be setting up some classes in C++ to implement a simple directed graph. It's one of the more common data structures you'll see in computer science, and you'll definitely have to work with it during classes and job interviews. If you happen to be in the field of compilers, like me, it's pretty much all that you work with. So in this video, we'll simply just set up some classes, like I mentioned, but in future videos, we will build on this and touch on more complex topics that have to do with directed graphs, like various algorithms. And as I've mentioned before in previous videos, I'll be using GitLab to host the repos that contain the code that I write during these videos. The link to these repos will always be posted in the description section of the videos, so no worries. For all of my C++ videos, their code will be in the repo called CPP, and the code for each episode will be in its own branch. So for example, as shown here, you can see the branch called cmake_setup, which is the branch for the video I made last time, which was about setting up a C++ project with cmake. For this video, we'll be using this branch here called directed_graph_setup. I'll be cloning this repo with SSH like this, but you can also download the repo as a zip file by clicking on these buttons like here. Okay, so I'm gonna clone the repo like this, and as you can see, we have these arithmetic files from the last video. So recall that the proper way to build this project is to run cmake, cmakelist.txt, and then run make. The first thing I'm gonna do actually is to just remove these files from the last video, and these lines in main.cpp because we won't need them for this video. So now you can see that all we have in the src directory is just main.cpp. Alright, now let me just copy and paste a brief description of the kind of graph that we want to support. If you ever do a technical interview for a company and they ask you to implement a directed graph, they'll probably give you a written statement like this. So this will be a good opportunity for you to prepare for those interviews if you have them in the future. And as I've mentioned before, we want a directed graph, meaning that the edges in the graph have directions. So an edge pointing from some vertex u to some vertex v is not the same as an edge pointing from v to u. Some additional properties that we want. The first is that for any pair of vertices u and v, there can be at most one edge pointing from u to v, which means that u cannot have multiple edges pointing all to v. And in other words, the graph that we are building is not a multigraph. And two, each vertex has a unique ID and an int data that's associated with it. And then three, edges are unweighted and they don't have any data associated with them. Now, here are the required public methods that this class must support. One, some method to add a vertex to this graph. Two, some method to add an edge. Three, some method to remove a vertex, which removes the vertex, all edges pointing to it and from it. 4, remove an edge. 5, get all vertices in the graph. 6, get all vertices that some vertex points to. In other words, these also go by the name of successors of that vertex. And then finally 7, a string representation of the graph. So here it says the string representation must be deterministic. What I mean here is that no matter how many times you run the function or the program, you get the exact same string every single time. So this means that every time you go to print your graph, you have to print the vertices and the edges of the graph in the exact same order every time. You'll notice that the descriptions of a lot of these methods are left pretty open-ended. And one reason I wrote them that way is because that's how most interviews actually go. They do this on purpose because this requires you to actually make your own decisions and your own judgments, and they want to see how you think through the design process and what kinds of things you consider, like trade-offs. Okay, so let's make some files to get us going. I'll make a directory called directed_graph in the src directory and create directedgraph.cpp and hpp. So after that, the src directory looks like this. Now recall that after adding or removing files, you can't just run make. You have to run cmake first and then run make.
So now you can see that we're actually building the directed graph that we have just added, and there are no build failures. Now, throughout this video, I'll be running make through Vim like this. Vim is the editor that I'm using, that I've been using to edit the code. But just keep in mind that this is exactly equivalent to running make from the command line manually that I've shown. So don't be alarmed if the results of running make on my screen looks a little different from yours. Okay, so let's copy the description of the class to the header file, and from here I'll basically walk you through how I would go about designing data structures like these in real life. The first thing you should do with any header file is to add the pragma once, and before we go further I wanted to show you one more thing. So if I type this into the header file, this should fail the build, right? But actually you'll see that no build failures occur, like shown here. So this is because remember that header files are not really considered by the compiler unless it's included from a CPP file. So in order for the compiler to see this change and actually compile the changes that we made to the header file, we have to go to the, well, any C++ file, but we're going to go to DirectedGraph.cpp and include this header. Then we run make, and you'll see that the build fails as we've expected, and now we know that whatever change we make to the header file will be compiled. Okay, so for the classes now, we'll create a class to represent the graph itself called DirectedGraph, and we'll also create one for the vertex. So since the class doesn't require edges to hold any data, for this video we won't create a class to represent the edges explicitly, but we will create one in the future when we might want the edges to hold data. Alright, so I'm going to start by copying the sections of the descriptions to the classes that they belong to. Alright, so the vertices in this graph will require a unique identifier and an associated data. So I'll start by creating getters and setters for each. Now this is something that I like to do personally, which is that right now if you run make, the build will fail because it's not valid C++ code that we wrote just yet. So I like having frequent compiler feedback when I write code, make incremental changes in order to kind of iteratively refine it, like very small steps at a time. So what I like to do is first get the code to be at a state that's just enough to compile, even if it means that the types are wrong. And now, knowing that the code will compile, I can start making actual changes, because the first moment I do something wrong, the compiler will tell me, and I know that the error is because I made a mistake, not just because I haven't written all the boilerplate code quite yet. One thing I forgot here is to write a constructor. Now let's look at what we have so far. Specifically, let's look at the fact that we have an empty constructor, a constructor that takes no arguments, and we have a getter and a setter for the ID. If we define the interface this way, which we can, the users of this library might end up writing code like this. They create a vertex, and they set the ID, and they set the data after the vertex has been constructed. Which is fine, but let's look at that point in the program right there between the construction and the set ID. What's the ID in the data of the vertex that was just created? It's probably set to some default value like 0 or -1. Those are some common choices. But it's almost certainly the case that most users will consider this ID to be invalid, or at least they'll know not to use this vertex because it's not ready yet. So in other words, this vertex is in an invalid state. Now, as programmers that want to write safe code, we always want to minimize the time that the data structure spends in an invalid or undesirable state. Ideally, the data structure is in a valid state all the time. So how can we rewrite the interface to accomplish this? The first thing we're going to do is we're going to rewrite this constructor so that it takes an ID and a data. And the second thing we're going to do is we're going to remove the setID method altogether. Now it's impossible for a vertex to have an invalid ID because every vertex can only have one ID throughout its lifetime because it cannot be reset. And unless the programmer wants it to always have an invalid ID, they have to provide a valid ID at the moment of construction, which means that all vertices always have a valid ID. So this is a great example of designing the interface of your library in such a way that it encourages safer programming practices. But It's got to be a careful balance, because if you take this too far, the library becomes too hard to use, and the users may not want to use your library no matter how safe it is. Alright, now let's go ahead and fill out some more type information. I'll use size t for the IDs so that I don't have to deal with negative numbers. And a non-static member method for getting the ID of a vertex can and should be const qualified. Now the data is int, and getters can be const qualified again. One programming practice that I preach all the time is to mark things as const unless they need to be mutated. C++ encourages programmers to write non-const code because the default for things is to be non-const. Like if you want things to be const, you have to opt in by writing the const keyword. There are languages out there that work the opposite way, like Rust, where things are constant by default, and then you have to opt in to make things mutable. I'll delve into this topic a lot more in the future, but for now, let's just write everything as const unless they need to be non-const. Let's make that our simple rule. Although these weren't specified, let's add some more methods that are nice to have. So the first is toString, that generates some string representation of this vertex. And the second is to override the == operator to make it more explicit that vertex IDs should be unique. And by considering vertices as equivalent, if their IDs are the same, we are enforcing this concept more. Now, before we talk about what kind of member variables, in other words, data, this class should have, I really want you to notice that I defined all the functional interfaces before I considered anything about the member variables. So this is pretty important philosophically. The functional interface of a class should dictate the kinds of data structures used in that class, but not the other way around. You should never decide on the data structures first, then try to come up with some functional interface that fits those data structures. But in this case, the class is simple enough. We just have a size t for the identifier and int for the data. The data structures that we'll use is more complicated for the graph class, so what I just said will be more applicable then. And the build failure. I try to leave these honest moments of mistakes and hiccups in the recording because you might run into these yourselves. My hope is that by me leaving these moments in the video, you'll get a glimpse into how I debug and fix these errors so that when you encounter them, you'll have seen them before. And in this case, the compiler is complaining that it doesn't know what size t is, and for various reasons, I guess size t is not a built-in type in the C++ language. You have to import some header from the standard library that has size t defined so that you can then start using it in your code. So in this case, there are actually two problems. One is that the compiler doesn't know where size t is defined, and the second is it doesn't know how to make sense of standard string. And to use standard string, you have to import this header, include the header called string, which happens to include other headers that define size t. So by just including string, you can actually solve both of these errors at once. Okay, that's about it for the declaration of the class Vertex. Now let's move on to the DirectedGraph class. So in this case, it's straightforward which methods we need to write because it was given to us. Here is the list of required methods. And I'm going to do the same thing I did before, which is to write all these methods with the names that we want, but with the types as void. This is so that the code compiles so that I can make small incremental changes with the compiler's help. Except for the toString method because it's simple enough that I can just write it in one go. And okay, so you can see that it compiles now. Okay, so the first method we're going to look at is add vertex. I'm just going to go ahead and copy the description from above. Okay, so the idea behind adding a vertex is pretty simple enough. You just add a vertex to the graph. But there are some nuances to how you can do this, so I want to consider them all. The first way you can write it is like this. So you take a pointer to a vertex. This implies that whoever wants to add a vertex to your graph needs to create the vertex first themselves and then pass the created vertex to your graph. One problem I can think of, although this wasn't mentioned explicitly, we don't want vertices to exist in multiple different graphs. The way it's written right now, This allows users to create a vertex, add it to a graph, and add it to another graph as well. While this might be okay in certain circumstances, in our case, we want to make things simple, so we're going to disallow that. An easy way to solve this problem is for the graph to create the vertex for the user, instead of taking in a vertex that was already created. So we can rewrite this addVertex method to take in an ID and a data so that it can create a vertex from within its body. Now with the method written this way, this means that the users of this library will write code like this. They will initialize a graph and they will add vertices with different IDs and different data. Okay, so now we've solved the problem of the same vertex being in multiple different graphs. But we still have another problem, which is with regards to the guarantee that we make that every vertex in the graph will have a unique ID. So with this design, who is responsible for making sure that this holds true? The answer is, unfortunately, the users of the library. The users need to make sure that ID1 and ID2, as shown here, are different to make sure that every vertex has a different unique ID. So it's no longer a promise or a guarantee that every vertex has a unique ID. It's more of a burden to the user that they need to uphold that constraint in order to use this graph. And that's not good. So what we are going to do is rewrite this method like this. We're going to have the addVertex method only take data as the argument. And we're going to make the promise that the addVertex method will not only create a vertex for you, but it will also make sure that the created vertex has a unique ID. So the users of this library no longer have to worry about making sure that each vertex has a unique ID. And of course, we're going to declare the int data as const because it does not need to be mutated. And one more thing, since we are creating the vertex for the user, we should return a pointer to the vertex when this function is called, so that the users have a way to refer to these vertices that were just created. Next up is addEdge, which adds an edge between two vertices in the graph. Since in this case our graph is a directed graph, we add an edge from a specific vertex to another vertex. The direction matters. One thing that we will require is that UNV exist in this graph because it doesn't really make sense to add an edge between vertices that don't exist. So remember that this graph cannot have multiple edges going from some vertex u to some vertex v. So we need to handle cases when a user tries to add an edge from u to v when it already exists. So if an edge from u to v already exists, we'll say that nothing will happen to the graph. And otherwise, meaning there is no such edge thus far, we'll add the edge. And now, since we're adding an edge between two vertices, we need to take those two vertices in as input. So one thing we can do is take both of them in as vertex pointers. And we might want to give the user some indication whether this edge ended up being inserted or not. So we're going to return a bool value from this function. So we'll return true if this edge was inserted, and we'll return false if nothing happened and the edge was not inserted. One other thing that I care a lot about is trying to use pointers as little as possible. So instead, we're going to take these two vertices in as references. This has a lot of benefits, one of which is that from inside of the function, you don't have to worry about the pointer being a null pointer. And also it makes things simpler and just nicer to work with. And we'll make the project now, and you can see everything's good so far. And now on to remove vertex. So all it does is it just removes a vertex and associated data. So we're going to take a single input parameter of a vertex. And just like before, we're going to take it in as a reference instead of a pointer. Now, it is possible that a user tries to remove a vertex that does not exist in the graph. So we're going to do something similar. So if this vertex exists in the graph, we will remove it. If it doesn't, we'll do nothing. And similarly, we'll return a Boolean value to indicate whether or not the vertex was actually removed or not. And moving on to remove edge, very similar. So we're going to take two vertices in, and we're going to try to remove the edge. If the edge exists, we'll return true to indicate that it was in fact removed. and we'll return false if the edge did not exist and we did nothing to the graph. And next is get vertices. This is pretty simple, just return all vertices in the graph. So we'll just return a vector of vertex pointers.
Okay, now let's just think about how the users of the library will use this function. So consider this example code where the user calls this method to get all the vertices in the graph and tries to do things with them. In this case, they can modify the vertices themselves because the pointers that are in the vector point to a non-constant vertex type.
Now let's change this function slightly so that the DirectedGraph DG is passed in as a constant reference. For one, we can't even call the getVertices method because in the function handle_v2, the DirectedGraph instance is const qualified. But just for the sake of discussion, let's assume that you could call getVertices even if your instance of the DirectedGraph class is declared constant. One thing I want you to think about is, should you be able to modify the vertices that is returned by the getVertices method when your DirectedGraph class instance is declared constant? Well, this is almost a philosophical debate and many people have different opinions, but I personally believe that when the data structure, in this case DirectedGraph, is declared constant, you should not be able to modify anything about that graph. So ideally, you should not be able to modify any of the vertices that were returned by the getVertices call if your DirectedGraph class instance is declared constant. So how can we rewrite this so that when the instance of the DirectedGraph class is constant, we disallow users from modifying any vertex that is returned by this function? The answer is constant overloading. So we are going to declare two getVertices methods actually, and they're going to be slightly different. So the top one is going to return pointers to non-constant vertices when the instance of the DirectedGraph that calls this method is non-constant, and the second returns pointers to constant vertices when the instance of the DirectedGraph that calls this method is declared constant. So although we're returning a vector of pointers in both of these methods, in the second case we return pointers to constant vertices, which means that the users cannot modify the vertex through that pointer. Next is get successors. So given some vertex u, we're going to return all vertices that u has an edge pointing to. And similarly as before, we're going to constant overload this method so that when the DirectedGraph instance that calls this method is constant, we return the successors, but as constant successors, pointers to constant vertices, so that the users may not modify them. And finally, we have the toString method. So for this, remember, all we need to do is return some string representation that is deterministic, which means no matter how many times you run this method, you get the exact same string every time. So the way we are going to enforce that is by returning the string that shows the vertices and edges in sorted order. So what I mean by that is we're going to sort all the vertices by their ID, and then when we print the edges, we're going to first sort by the source vertex, and then after that we're going to sort by the destination vertex. Let's look at an example real quick. So we're going to return a string, but it's actually going to be multiple lines. The first line is just going to say DirectedGraph, and the second it's going to have a little indent, say vertices, and then print all the vertices in order. So you can see that V0 gets printed before V1 because we sorted them by their IDs. And when we go to print the edges, we will first sort by the source vertices, and then we're going to sort by the target vertices. So once again, notice that we have defined all of our public methods first. That's the very first thing we did for the class. Now we're ready to come up with the data members of this class that will help us make these public methods actually work. So remember that one of the promises that this class makes is that every vertex will have a unique ID. So we need at least one data member to help us accomplish that. And in this case, we can do that by having a counter that counts from 0 and up, so that every time you add a vertex, you can simply increment the counter and use that as an ID for the next vertex. And that helps us make sure that every vertex that gets created does not share the same ID as anything that was created before. And next, we're going to need some kind of a container to hold all of the vertices that were ever created by this graph, for this graph. And lastly, similarly, another container that holds information about the edges in this graph. Okay, so the first thing I'm going to do is I'm going to have the ID, the vertex counter, to be represented as a size t type instead of an int. That's just so that we don't have to deal with negative numbers as IDs, and that just feels nicer for me. And notice that I'm prefixing all the data members with m underscore. This is just so that from within the methods, we immediately know which are the data members of the class versus local variables. Now, for the container of all the vertices in this graph, one thing we can do is we can have a vector of just pointers to instances of the vertex class that we have created. There are pros and cons to this. The most obvious con being that this encourages us to do manual memory management, meaning you use the new keyword to allocate memory, and you have to remember to use the delete keyword to free that memory. And that's not really ideal. Part of writing good C++ code involves using modern ideas and concepts, and one of those is automatic memory management using smart pointers. So we're going to do that by instead having this vector hold unique pointers instead of raw pointers, so that we never have to worry about remembering to free the memory that we have allocated. Now, this design of holding a vector of unique pointers is okay for now, but later in the video we'll come back to talk about ways to improve this perhaps. And for the container of edges, we can have something like an unordered map that maps vertex pointers to a vector of its successors. In other words, given a vertex, what are the other vertices that that vertex points to? And this is a pretty well-known pattern. This also goes by the name of an adjacency list representation of a graph. A couple things. The first, this design is not optimal right now, but we'll have it like this for now, and we'll come back later to improve upon it. And second, this might be a bit confusing if this is the first time you're looking at an adjacency list representation, but there is no actual data type that represents the edge. The edge is implicitly there by the fact that in this map, a vertex points to other vertices, which implies that there must be an edge between them. And so now we'll just go up to the top of the file and include the appropriate headers for the different data structures we're using, like vector, unordered map, and etc. And we'll just make sure that everything compiles and is well. Okay, so we're done with the header, so let's just copy a lot of these over to the C++ file, and we'll start implementing these. Yeah, so usually what I do is I just copy the whole header file over, and I just write the class name, ::, in front of every method name, and go from there. I've mentioned this before, but if we build this project right now, obviously it fails because we didn't write valid C++ code. So similarly as before, what I'm going to do is I'm going to fill out just enough information in the body of these methods so that they compile, and then go from there in order to make iterative small changes. So what I do to accomplish that is first I just create the body of the method and return the simplest dummy value that I can return in order for the code to type check. So in the case of pointers, I just return null pointers. In the case of bools, just return true or false, doesn't really matter. And in the case of vectors, just return an empty vector using this initializer list syntax. And you can now see that this compiles. Now, one thing that I want to make sure though is that I remember to come back to finish implementing these functions. I don't want to think that these are valid and this is what I wanted it to be. So the way we're going to do that is we're going to add this assert false, which fails unconditionally. By adding this in front of every return statement that I just added, what it does is it guarantees that whenever this function is called, it fails, which kind of serves as a reminder for me to come back to these and finish implementing them. And to actually use assert, all you have to do is you have to include the header called cassert, And you can see that it compiles now, so we're good. We forgot to bring over the Vertex class, so we're going to copy that and essentially do the same thing we just did to the DirectedGraph class. Basically just return dummy values, make sure it asserts, and make sure it compiles before we actually start implementing them. Alright, so now things compile and we are ready to start writing actual code to implement the Vertex class. The first thing we're going to do is we're going to implement the constructor of the Vertex class, and we are going to initialize the member variables of this class using the member initializer lists, which is this colon kind of syntax that you're seeing right here. This is the preferred way to do things in the newer C++. We won't go into too much details in this video, but just know that this is the better way to do it, rather than in the body of the constructor explicitly saying things like this arrow m_id equals id. Alright, then moving on, vertex get id. This is pretty simple. You just return the id, and since we're returning by value, we don't need to worry about mutation in this case. Same thing with data, just return the member m_data, that's it. And for set data, also pretty simple, just make sure to assign that passed in value to the member variable. And for the toString method, I'm just going to arbitrarily decide that when vertices are turned into strings, it turns into the string v followed by the ID of the vertex. And next, for the equality operator, we'll simply compare the ID of the current vertex and quote-unquote that vertex. And if they equal, then the vertices themselves are also considered equal. And one thing I forgot to do is make a constructor for the directed graph. So I'm going to do that and copy that over to the CPP file. Okay, so we just have these three data members to initialize. The counter we will initialize as 0, and the other two vectors and the map we will just use the default constructor with no arguments. Okay, so now add vertex. We basically just need to create a vertex, make sure it has a unique ID, make sure it's added to the graph, and return the pointer to the created vertex. Okay, so the first thing we need to do is create a vertex. The way we will first try to do that is by using the unique pointers constructor, by passing in the pointer, raw pointer, to a created vertex that you have created using the new keyword. And the way we're going to make sure that it has a unique ID is by incrementing the counter after this vertex has been created. So what this does is it makes sure that the next vertex that gets created will have a different unique ID that's different from every vertex that has been created before it. Now we will add it to the graph by adding it to the vector that holds all vertices. And we have to use standard move here because remember that unique pointer is a move only value and it cannot be copied. And lastly, to get the raw pointer to the vertex that we just created, one thing we can do is we can use the back method on the vector to get the last element, which is the one that we just inserted. And then we can do the get call to the unique pointer to get its raw pointer that it manages. The reason we have to do this is because the variable vertex has been moved because of the standard move call, so it no longer refers to the same unique pointer that we are expecting. And we try compiling it and everything compiles and everything's good, but let's try to make some more improvements on this code that we just wrote. The first is how we create the unique pointer. What we just wrote is accepted, but there's a better way to do it. So the bad thing about how we're doing it right now is we are still manually allocating the vertex using the new keyword. In the most ideal scenario, we never use the new or the delete keyword to really get us to not manually handle memory. So what we can do is we can instead use standard make unique, which does essentially the same thing as the code that we just wrote, except that it is less verbose, has better performance, and third, it really gets us to avoid using the new keyword. And the last thing, I'm kind of nitpicking, but it's the way we grab the raw pointer to the vertex that we just created. Right now what we do is we look at the back of the vertex and then we get the raw pointer. The first problem I have is that the connection of this line to the fact that we're trying to grab the raw pointer to the vertex that we have just allocated, that may not be clear. If I'm looking at this code for the first time, I might wonder, why are we looking at the back of a vertex? So to make it more clear, have the code be almost self-documenting, what we can instead do is we can create a separate variable called raw pointer, and then have that raw pointer store the, you guessed it, raw pointer to the vertex that we just allocated. And instead of looking at the back of the vertex, we can simply just return this variable at the very end of the function. Now it's more clear what it is that you are actually returning. And an added bonus to doing this is that it's one less function call. You no longer have to call back on the vector, so it helps us do as little work as possible. All right, now add edge. So we want to add an edge that goes from U to V. First thing we're going to do is we're going to require that both of these vertices exist in the graph. If not, we will error out. So the first thing we're going to do is if we're going to check if an edge already exists between the vertex U and V. So if it already exists, we're going to return false and do nothing to the graph. Whereas if that edge does not exist, we will add it and then return true. Okay, to check that these two vertices exist and to error out in the case they don't, we're just going to use assert. Now, so we want to assert that U exists, and we also want to assert that V exists. Now, to do this, what we need to do is just go through our vector that holds all vertices in the graph and check if these two exist. Now, this is extremely time-consuming. Because we have a vector, we have to go through every element in the vector to check if these vertices exist. In other words, this runs in linear time with respect to the length of the vector. Usually linear time is okay, but in this case it's a big no-no because there are simple tricks to bring that time way down to logarithmic or even constant in average case. And that trick is to use unordered map. So what we're going to do is we're going to have an unordered map whose key is a raw pointer to a vertex, and it maps to a unique pointer, same as before. So the reason we are doing this is so that when users pass in a reference or a pointer to a vertex, we want to be able to check as rapidly as possible if that vertex exists in this graph. Now, the reason we're not using unordered set here is because what the user passes in is not a unique pointer. So that's why we have to kind of use a map that maps from raw pointer to a unique pointer to make sure that we don't expose this fact that we're using a unique pointer to the end users, because they don't really need to know that we're using a unique pointer. Okay, so with this change of data structure, now we are able to check that a vertex exists in our graph or not in constant time in average case. So the first place we need to modify is add vertex, because we're no longer just adding a vertex to a vector. We are now adding it as a value in a map. So instead of just pushing it to the back of a vector, what we're going to do is we're going to map the raw pointer to that unique pointer in our unordered map. So I'm choosing to use in place here in order to create a key value pair instead of using the square bracket operator that we are very familiar with. There are different reasons I'm doing this, but in this case it's to avoid any kind of copying of the unique pointer. So when you're working with move-only values, try to use in place when you can. Now we are going to do something very similar, which is first to assert that vertices U and V exist in this graph. And thanks to the change of data structure that we just made, we'll be able to do these checks both in constant time and average. All right, now we have to do this conditional handling. The first line I'm actually going to write is auto-reference. U successors is edges square bracket pointer of U. So there are some nuances here that we need to pay attention to. The first is we're using a square bracket operator for a reason instead of using .at. So what the square bracket operator does for an unordered map is if the key does not exist, it creates a value for that key using the default constructor. So in this case, if the pointer to U does not exist, it'll create an empty vector in the unordered map. And the second is that uSuccessors has a reference type. We'll get to this in a little bit, so we'll just move on for now. So now we'll try to find the pointer of v inside of this list of successors. And then if we found v, that means the edge from u to v already exists. So we're going to do nothing and return false. Whereas if that edge does not exist, we're going to do something like return true and insert the pointer of v into our vector to signal that we have created this edge. So you might have noticed that I wrote uSuccessors.find u instead of v. So that's a typo that leads to a bug later in the code. But for now, let's just imagine that you're all in my shoes writing this code when I didn't realize that I mistyped it, and let's just go along with it for now. All right, so we'll get rid of this insert call just for now, just to illustrate a point. If we try to compile, you'll see that the build fails. And the build fails because it says vector does not have a member called find. So we can't do this .find with the vector because it doesn't support it. So that's not that big of an issue, but the bigger issue is the performance of this. So if you try to find an element inside of a vector, even without using this .find call, realize that it takes linear time, which is, as we've discussed before, not that great. So one thing we can do is we can go and change this vector to instead be an unordered set, which allows us to find any element in the set in constant time, an average. And after you make this change, make sure to include the unordered set header at the top of the header. Okay, so now if we go back and compile again, you'll see that everything works. And not only does it work, it also works better because it runs faster now. And now we can add back this insert call and everything is good now. And once again, just remember that the uSuccessor.find u, that's a typo, and we'll get back to it later in the video. Okay, now we'll implement remove vertex. So I'm just going to copy these requirements down there. So basically, if the vertex u exists, we want to remove the vertex, remove all edges pointing to it and from it, and then return true. Whereas if the vertex u does not exist, we want to return false and do nothing. So we're going to try to find the pointer to the vertex u inside of the m vertices. I'm going to fill out the else case first because it's simpler. Now if it exists, the last thing we want to do is we want to return true. And to remove the vertex, all we have to do is use the erase call. We're going to erase it from the list of vertices and remove all edges pointing to the vertex. This will be a little more complicated, so I'm going to do the third one first. Remove all edges pointing from the vertex. That's simple. So we have the data structure such that it's really easy to grab all the vertices that u points to. So if we just call the erase method with u, what that's going to do is it's going to erase the set, which represents the vertices that u points to. So with this one call, we can take care of this step altogether. Now this next step is going to be a little more involved, so we have to remove all edges that point to u. The way we have things set up, the best way to do it right now is simply just to go through every key value pair and see if any of the vertices point to u. And if it does, then just get rid of the u from the set, which is the value of the pair. We can do this a little more efficiently by adding more data structure to this class, but for now, we'll just make things simple, and this is where we'll leave it. Okay, so everything compiles and we're good. I'm just going to add another little comment here before moving on. Okay, so next thing is just removing an edge between two vertices. So this is a lot simpler. So first thing we're going to do is we're going to check if both of these vertices exist. If they don't, we're not going to do anything. Now, if they both exist, then things are a lot simpler because we now know the exact starting point and the end point of this edge that we're trying to remove. So we're going to just find the set of vertices that u points to. Then if v is in that set, we're going to remove it. If v is not in this set, the edge does not exist, so we don't need to do anything. And you'll notice again that I'm using the square bracket operator here. That's on purpose. If I didn't use that, then I would have to use the .find call to see if this key value pair exists. And that's going to look a lot uglier because that turns into like 3 or 4 lines of code. And I'm just going to get rid of the assert and the return false, and we move on. So next is get vertices. This is, again, pretty simple. We already have a map, m vertices, whose keys are the entire set of vertices that are in this graph. So all we need to do is just copy those keys of the map to a vector and return that vector. Okay, so one more thing we're going to add is vectors, as we know, they are implemented in such a way that if you just keep putting items into it, it will resize itself to make more room to accommodate for more items. And if that happens over and over and over, that can get pretty expensive. So what we're going to do is we're going to add this reserve call, which pre-allocates the vector to be large enough to hold however many items that you specify. And this works in this case because we know ahead of time exactly how many vertices there are, which means we're going to know exactly how big the vertex needs to be. So by adding this call, we are preventing ourselves from doing unnecessary memory allocations, which speeds up the program. Okay, and for the constant version of this method, we're just going to copy the whole thing, just change the declaration to be constant vertex pointer. Okay, now getting the successors of u. We're just going to get all the vertices that u points to and copy it to a vector and return it. We need to copy it to a vector because right now we're storing these successors as an unordered set. So we need to explicitly pass in the beginning and the end iterators of the set to the vector constructor in order to copy it before returning it. And also note that I'm using the square bracket operator so that we create this unordered set in case u does not exist in the map. Okay, now for the constant version, we're just going to copy over this exact same code. But when we run make, you'll realize that things no longer compile, even after we add this const there. It's because the square bracket operator I've already mentioned creates a value for a key that does not exist yet, right? So that requires modifying the data structure, which then requires the data structure, in this case the map, to be declared as a non-constant. So since we can't use a square bracket operator, unfortunately we're just going to have to do explicit checking of whether or not u exists in this map. If it does, do everything we did before, which is to copy the successors to a vector and return it. But if it does not exist, then we're going to have to just explicitly return an empty vector like this. And notice here that we're using the .at operator here. The difference between the square bracket and the .at is that square bracket, if the key does not exist, creates a default value, whereas .at simply just errors out. Okay, now the last method we need to implement is the toString method. This is probably going to be the most complicated one we've written so far. But basically I'm just going to keep a string and keep concatenating strings to make a bigger string that we will eventually return. There are more efficient methods to do this, for example by using string buffers and whatnot, but in this case we'll just use strings just to keep things simple. So remember, what we want to print is we want to print the vertices first in sorted order, and then we're going to print the edges also in sorted order. So I'm going to start out by just having a string that we will build, and it's going to contain the very first line, directed graph, colon, and then a new line character. Okay, then what follows is the two spaces followed by vertices, colon, new line. Alright, now the way we're going to print all the vertices in sorted order is by first grabbing all of them by using the getVertices method that we have implemented. And then we're going to use standard sort to sort through these vertices. And with sort, you can provide your own lambda function that is essentially a custom function to compare two items in whatever container it is that you're trying to sort. So here we need to provide this custom compare function because the compiler doesn't really know how to compare two instances of the vertex class. You know, given two vertex classes, how do you know one should precede another in an ordering? One thing we can do is to go back to the vertex class and implement some methods that will hint the compiler how these instances should be compared. But what we're going to do for now is just make it easy for ourselves and provide this function that basically says one instance of vertex should precede another if its ID is less than the other vertex's ID. And we just have to remember that standard sort comes in this header called algorithm, so we just have to make sure to include that. And I'm just going to go back and rename the vertices to sorted vertices so that it's a little more clear that they have been sorted. Okay, so now all we have to do is just iterate through this vector, sorted vertices, and print each vector one by one. And we have already implemented the toString method in the Vertex class, so we can make use of that here. Okay, and in order to print the edges in sorted order, we can make use of this sorted vertices. If we can treat each vertex in the sorted vertices as the source vertex, then all we have to do is get the successors of that source vertex, then sort those successors, and then print it in that order. Then what we'll have is a printed list of edges that is first sorted by the source vertices, and then sorted by the target vertices. Okay, so if a vertex has no successors, then we don't have to print anything, so we're just going to do nothing here in the else case. But we're going to run into some issues here. So we're using vertices that are in the sorted vertices vector. I've been using auto a lot, so it's hard to tell the type, but it has the same type as the return type of get vertices. And realizing that we called this get vertices method under a constant context, the type of sorted vertices is actually a vector of pointers that point to a constant vertex. Now this will cause issues as it says here, so no matching member function for call to find. So this is because M edges, as you can see here, is an unordered map whose key is of type vertex pointer. So the find method will therefore expect a key that is a pointer to a non-constant vertex, whereas U, we just established, is a pointer to a constant vertex. So there's this mismatch because we have something that is a pointer to a constant vertex, and we can't just convert that to a non-constant vertex pointer. So the compiler doesn't really know what to do here. A really easy, cheap solution is to get rid of this const right here so that when we call toString method, we're not guaranteeing that we are not going to modify the directed graph instance. But this is bad practice because turning something to a string should really be a constant method. So what we're going to do is instead of removing const, we're going to add more const. It's always better to add more const. In most scenarios, that's a personal rule that I like to follow. So we're going to go to where edges is declared, and we're going to change its type so that the key is now a pointer to a constant vertex. So this has two benefits. One is that it solves our problem, but two is again, this will be a topic for a different video, but more constness is almost always better. You'll be surprised in real-life programming how many bugs can be prevented by using more const throughout C++ code. And in this case, you can see that the code compiles even though we just changed the type of the map, and that's because pointers to non-constant data can be converted into pointers to a constant data, but not vice versa. Now we can go back and continue writing where we left off. So we will grab all of the successors of this vertex, sort them, and then print the edges. And notice that when I first get the set from the edges map, it's a set, but I have to create it into a vector so that when I go to sort it, that ordering can be preserved. Now what I'm going to do is I'm just going to iterate through the vertex and print the edges. Okay, so now we are basically done. One thing I'm going to do is I'm just going to reduce some code repetition by creating a helper function. Before that, I'm going to get rid of the assert and the return of empty string, and we're going to change that with return s, which is the string that we've been building. So I'm noticing that we sort vectors twice in this code, and there are a lot of similarities in the way that that's done, so I will factor those out into a separate function like I mentioned. The first simple thing we can do is, after noticing that the lambda functions that's passed into both of the standard sort functions are identical, I can simply assign it to a variable and just use that variable twice. So this is less writing and helps make the code less verbose. but I still notice that there's more that can be factored out. So for one, I'm noticing that you have to create a vector and then you have to sort it. But second, more importantly, because of how standard sort works, the vector that it operates on needs to be non-constant. So because of that, what we have here is that the vector sorted vertices needs to be non-constant even though it can be constant. So what are some ways that we can make this constant to minimize the chances that somebody could accidentally modify this vector?
One thing we can do is we can write a function that takes in a vector and return its sorted version. So the difference here is that we're not sorting the vector that's passed in, we're going to create another vector, and this new vector will be a sorted version of the vector that was passed in.
Now we could write the function that way. Now if we write that function, inevitably, since we're creating another vector, we'll be copying the contents of the input vector. So in the case below where we have a set that we want to sort, if we want to use that function, we would have to first copy the set to a vector, like we already do here, and then that vector will be copied once again inside of our sorting function. So that's a lot of redundant work, right? So the way we're going to solve this problem is by using the best practices of the C++ 11 standard, which is to use iterators. Okay, so what we'll do here is we'll declare the function like this so that we're returning vector of pointers to constant vertices, and the parameters will be 2 iterators. So let's see what this allows us to do. So from inside of the function, we can create a vector using a constructor like this. What this does is the vector constructor is taking in 2 iterators that specifies the range of elements that need to be copied into the vector. And what we can simply do is we can just sort this vector, since this vector already contains the copies of the elements that we want. And by returning this vector that was created from inside of the function, we have sorted the vector, the input vector, without modifying it. There are better ways to declare this function. So for example, the parameters can be universal references instead of a constant value, but we'll just ignore that for now. So here we can really see the advantages of using iterators as inputs rather than taking a vertex, because you can create iterators from a lot of different containers, vectors, also sets. So using iterators gives you a way to write a function that can handle a variety of containers, not just vectors or sets. Okay, now we can go back and replace all this sorting logic with the function we just wrote. So we just have to make sure to call the function with the beginning and the end of the container that contains the data we want to sort. I'm just renaming the containers to indicate that the data has already been sorted, and now the build passes, and I'll just get rid of some variables that are not used. And just to recap what we just did, we wrote our sorting function using by taking in iterators as inputs, and that allowed us to use one function to handle both vectors and unordered sets. Okay, so that is it for our implementation of the directed graph. We're going to finish off the video by writing a test case to verify that our functions, the functions of the class directed graph, is working as intended. Now, in real life, you would use libraries that are out there that helps you actually test your code. But for this video, just for the interest of time, I'm just going to write my own tester. Basically, we're just going to grab the result of some computation. In this case, I'm going to build up a graph and call the toString method that returns a string representation of the graph. And I'm going to compare that to what I expect that string to look like. And if those two match, then I'm going to go ahead and assume that everything is working as expected. And if the two strings don't match, then I'm going to use assert to forcefully crash the program to signal that some test is not passing. So to be able to use the directed graph class, we have to make sure to include the header as shown here. I'm just going to build it to make sure that we are doing everything correctly. And what I'm going to do is I'm going to create an empty graph. And to that empty graph, I'm going to add some vertices. So I'm just creating 4 vertices. It's not too important how many or what kind of data they have, but I'm just going to add 0, 1, 2, 3 as the data of each vertex. And I'm going to put them into a vector just to keep track of them. So now I want to add the edges to the graph. So in this case, I want to add 5 edges. The first one is V0 to V0. That's a self loop. It's an edge coming out of V0 that points back to V0. Second is V0 to V1, and then V0 to 3, 2 to 3, and then another edge from 2 to 3. I'm adding this last edge V2 to V3 twice just to make sure that duplicate edges are not allowed in the graph. And I'm adding the edges like this by using the fact that V0, is, the index of V0 in the vector we created, Vs, is 0, and V2 is at 2, and etc. Okay, now I'm going to create a string, which is what I expect the toString method to return at this point. So you'll notice I'm writing down the vertices in alphabetical order, and same for the edges. I am writing them down in the order that I talked about earlier in the graph. Now all I need to do is I need to just change that assert to do result equals expected. So if result does equal expected, that will return true, and the assertion will pass. Whereas if it returns false, the test will fail and the overall program will crash. Okay, so if we build and run the generated executable, you'll see that the assertion has failed. So this means that the test is failing. So I mentioned this earlier in the video, but this is because of a bug that was introduced throughout the video. So what I'm going to do is I'm just going to show you how I would approach solving simple bugs like this, so that when you encounter bugs during your course of programming, you will have some tips to work with. So the very first thing I'm going to try is printing. So this is one of the most classic ways to debug, which is to print things and visually inspect what's going on. So in this case, you'll see that I get some printout, but I can definitely see that something is wrong. For example, all the vertices are there, but not all of the edges are being printed. So at this point, okay, I can definitely see something's going on, but how do I actually go about locating the code that is responsible for this mismatch? So what I usually do is I put print statements at appropriate locations throughout the code. So the goal here is to insert print statements in appropriate locations of the code, so that every time the code goes to modify our graph, it prints what it's doing. So this is important that I'm printing just when the graph is modified, because really that's all we need to care about is every modification of the graph. I want to see what is happening and why it might be happening. And that'll tell us that some modification is happening when we don't want it to, and that is where we probably want to introduce our bug fix. So you'll see that what I'm printing is somewhat helpful in explaining why things are happening and what is happening. So for example, here it says the name of the function, which is addEdge, and it also says the edge u to v exists, and comma returns false. So when this gets printed to the screen, I know where this printing occurs and what is happening, and also why it's happening. And I'm choosing to add these print statements in the addEdge function because from the printout, I noticed that there was a problem with adding edges, not vertices. And here, I just forgot to turn the vertices into pointers. I wanted to print the pointers of the vertex. Okay, so it seems like everything's printing fine. So we see what u and v are, well, rather, they're pointers, and then we see when they are added, and we also see when they're not added. So I want to point out this line right here. So this is the first time we're encountering these u and v, and I know that because u, the address for u has appeared twice, but for v, it's the first time that that address has
printed, which means that the edge u to v does not exist yet, but for some reason the code thinks that it exists. Okay, now I'm going to go back to the code that printed this and see what's going on. So it seems like what we're doing, from the comments, it looks like we check if the edge exists, and if it does, we do nothing. And the way we're checking if that edge exists is by, looking at the u successors, and we try to find the address that points to u. Okay, so that is the problem. So what we're really looking for in the set of successors of u is we're looking for v. But in this case, we're looking for u. And I mentioned this earlier in the video, but this is a simple typo. So if we change that to v and we build and run the program again, we get the following printout. Okay, everything looks good. So it seems like the printout looks fine, but the tests are failing. So let's just go through and remove all of the printing lines because we don't need them anymore. And let's look at the printout a little closer. So I'm just going to run it again and copy and paste it right next to the expected strings so we can compare them a little more easily. And it just seems like in the expected string, I put colons next to the vertices and the edges, and that's what seems to be causing the mismatch. So I'm going to go ahead and remove those colons. And now you can see that the tests no longer fail. So the last thing I'm going to do is I'm just going to move all of these testing logic into a separate function, because once we start having multiple tests, it's going to be important to keep the tests readable and maintainable. And the way we're going to do that is by creating a function for each test case. And while I'm talking, I'm just going to go through, and for each method, I'm just going to write down the algorithmic complexity of each function. That is one of the more important things in real life as you design classes. So I'm just going to play it in the background and speed it up, but you can feel free to go to the repo in the description of this video and check them out. So I hope that you enjoyed this video. I know this was a long video, but the idea was to give you a full picture of the kinds of things that I go through as I design classes, simple classes, in this case directed graph in C++. I hope that you got a good glimpse into the things I consider, think about, and the order in which I do things. So as always, if you have any questions or feedback, leave them in the comments and I'll do my best to answer them. And if you also have suggestions for topics you want me to cover in the future, also let me know in the comments. Thank you so much again, and I'll see you in the next video.